Hello from Los Alamos, New Mexico. I'm Nina, and I'm so excited to talk to you about Mars. The year 2021 is going to be an incredible year for Mars exploration. We already have several missions in place on Mars right now, including the Curiosity rover and the InSight lander. But just this year, we launched 3 new missions, including the Perseverance rover.
And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
The Chinese Tianwen-1 rover, orbiter, and lander. And also the UAE's very first Mars mission, Hope.
From the Jezreel Convention Space Center at 6:58:40.
I'd like to focus on the Perseverance mission because that's the one that I'm working on. So you'll hear a lot more about the goals of the Perseverance mission from Katie later on. But I'll just tell you that I'm so excited that the main mission of this rover is to look for biosignatures on Mars. So we're looking for signs of ancient life in a place called Jezero crater, which we think held a large lake. The major unanswered question in planetary science is, was there or is there life elsewhere in the solar system or even the universe? This is a really important, fundamental question that we'd like to answer, and Perseverance is going to be able to help us find that answer. So the first thing we need to do before we're looking for life itself is to understand habitability, so the environments in which life as we currently understand it can exist. This is something that the Curiosity rover has been doing. We found that there's quite a bit of habitable environments in its landing site. So now with Perseverance, we're going to continue that research to find whether or not this landing site is a habitable place. Once we determine habitability, then we can take the next step to say, can we see signs of life? And so it's easy when you're looking for macroscopic life, something like a tree or a dinosaur, we would recognize that immediately. But looking for microscopic life is a little more challenging. And of course, we have to ask the question, is this ancient life that is no longer there, or is it extant today? Is it living now? And those are 2 different questions that we are asking. Perseverance is really going to be focusing on that first question. Was there ever ancient microbial life in Jezero crater? We've learned so much about Mars from past missions. We know that it was once a wetter and warmer world that had rivers and oceans, putting down sediments and building up rocks and mountains. And we know that somewhere in its past that changed, and Mars is now a much more arid and desolate place. So this is something that tells us about how the environment has changed over time. Perseverance is going to help us put the pieces of the puzzle together. We know all of this about Mars, but now, can we find materials that will tell us definitively if there were ever microbes on Mars? And the way we're going to do this is so exciting. We're going to do, for the first time ever, sample return. So even though we've gone to Mars many times and we have so much data from Mars, it was all done remotely. What we're going to do now is actually pick samples and cache them. So we're going to put them in a little pile with the Perseverance rover, and then we're going to send another mission in the future to grab those and actually bring these samples back to Earth. And this is just thrilling because we have amazing rovers on the surface of Mars, but they can only do so much. Whereas in our laboratories, we can make measurements and new measurements, and even measurements with techniques we have not yet invented. The Perseverance rover has an incredible payload of 7 science instruments, so I'd like to tell you about each one of them. The first instrument I'll tell you about is the Mars Environmental Dynamics Analyzer, or MEDA. And this instrument is located on the mast, and it's our weather station. So this instrument has a lot of different sensors, but essentially it's looking at the wind, it's looking at vapor pressure as it changes over time and over the day on Mars. And it also has a radiation sensor, so it can monitor the radiation environment. This is not just for purely science sake, it's also so that we can support future human astronauts on the surface of Mars. The next instrument I'll tell you about is Mastcam Z. And so these are two cameras that are located just under the rover's head on the mast. These cameras are incredible. They're going to give the most beautiful color panorama images. They're also going to be able to take 3D images, so you can see that with your red-blue glasses. And it's going to be able to take high-definition video on the surface of Mars. Now, it has the letter Z in it because Mastcam Z also will be able to zoom in. So this is a new capability. So you'll be able to zoom in on an area and really take a very high-resolution image of just one place. This is going to be incredibly helpful for our science, but it's also going to be in a great way to share with the public just how exciting Mars research is. The next instrument is the Mars Oxygen In Situ Resource Utilization Experiment, or Moxie. So Moxie is going to do something that we can do on Earth pretty well, but we've never done on Mars, and that is make oxygen out of carbon dioxide. And we're doing this for two reasons. One, we want to be able to demonstrate that if we send astronauts, we'll be able to let them breathe something. That seems simple enough. But really, the big point too is that we want to bring our astronauts home as well. And oxygen is a really critical component of rocket fuel. So what we're trying to do is to demonstrate that we can create rocket fuel out of Martian atmosphere to get our astronauts home. The next instrument is the Planetary Instrument for X-ray Lithochemistry, or PIXL. This instrument is on the arm. So Perseverance has only one arm and it's on the left. And so PIXL can touch a rock or just hover right above it. And what it does is it shoots X-rays at a sample and then looks at the X-ray fluorescence that comes back. And with those data, we can figure out the chemistry of that rock, but at a really fine scale. So we can look at it at sub-millimeter scales just to see what that chemistry is. It's going to be an incredibly powerful technique. The next instrument has a kind of a mouthful of a name. It is the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, or SHERLOC, which is a great name because SHERLOC is looking for clues that there was once life on Mars. So SHERLOC, as its name suggests, is using a technique called Raman spectroscopy to look for organic materials at a very fine scale. SHERLOC is located on the arm along with PIXL, and so like PIXL, we'll be able to look at rocks very closely. So the arm will move SHERLOC into place, and then SHERLOC can provide really detailed views of the organic chemistry of that rock. The next instrument is the Radar Imaging for Mars's Subsurface Experiment, or RIMFAX. This instrument is a ground-penetrating radar that will allow us to peek into the subsurface of Mars without digging any holes. So the way that this works is we use radar and we look at the return signal from this radar to see what it's reflecting off of. And we can see very clearly whether there is anything like ice or even water, which might take the form of a brine, a salty water. So RIMFAX is going to allow us to view Mars not just on the surface, but also into the interior. The last instrument I want to tell you about is my personal favorite because it's the one that I work on. It's called SuperCam, and it sits as the head of the rover right on top of the mast, and it has a cyclops eye that shoots a laser and vaporizes rocks, which is really cool, I think. So what SuperCam does is a lot. It has two different laser-based techniques. One is called laser-induced breakdown spectroscopy, or LIBS. This tells us the chemistry of a target. It also has a Raman spectroscopy instrument. So Raman gives us mineralogy or structures. We can also do a technique called time-resolved luminescence that will tell us trace elements. And we have a camera, the remote micro imager, that we can use to take very close images of the targets that we shoot with the laser. But not content to rest on our laurels, we also added a microphone to SuperCam that sits right on the masthead as well. So we have many techniques at our disposal on SuperCam. And the best part about it is that we don't have to touch anything to do all these analyses. We can make all of these measurements up to 7 meters from the rover. So that's over 20 feet away. So we can sit here in one place and just analyze all around us the chemistry and the mineralogy of the Martian surface. So SuperCam is so super because it combines all of these techniques at once. So we can examine the surface of Mars in many different ways. I want to tell you a little bit more about the combination of LIBS and Raman, these two laser-based techniques that SuperCam uses. It's incredible what they can do when they are combined. On our other instrument that's on Curiosity called ChemCam, we use the LIBS technique but not the Raman technique. LIBS provides us with chemistry information. But that's not everything that a geologist needs to know to be able to identify rocks. We need two things. We need chemistry and we need mineralogy. So chemistry are the elements. What elements are in this rock? And the mineralogy are, how are all of these elements arranged? What are the structures? So with LIBS, we can get that chemistry. What are the elements? And with Raman, we can figure out how those elements are arranged. And with those two techniques combined, we can come up with a unique identification of geologic materials. Another part of SuperCam that I think is really exciting is our microphone. So we put that on there, not just to hear what the Martians have been saying about us this whole time, but also to listen to the sound of the LIBS analysis. So the LIBS laser, when it hits a target, it makes a little snapping sound. Not quite a pew-pew, but absolutely audible. And so when you listen to the sound of that analysis, you can actually learn something about the target. And so as you hear that sound change, then you know things are changing about that rock target. So what I'd like to do is use that sound to find out whether or not there are rock coatings on Martian rocks. So why would we care about that, you say? A rock coating doesn't seem that interesting. Well, it's because a rock coating represents the relationship that a rock has had with the atmosphere, with the soil, and with water. And so that's what a rock coating is. It's a history of the rock's entire existence on the surface of Mars. And they're really thin. And sometimes, as geologists, we discard them because we want to see the rock inside. I think we're all really familiar with some kinds of rock coatings. If you've ever been in the desert, there is a very distinct shiny dark coating called rock varnish that's everywhere. And it's only a few microns thick. It's very, very thin. But it's actually an entire world in and of itself. It is a rich place where microbes live, eat, die, and reproduce. And this all happens in a teeny tiny space that we can barely see and step over like it was nothing. So if these environments are on Mars, this is a perfect place to look for the past existence of life. So what we can do with the microphone is to listen to the zapping sound and to hear a change in that sound that is indicated when you go through a coating. I've actually done some preliminary experiments at Los Alamos National Laboratory that has demonstrated that we can do this. And it's amazing. It's a subtle shift, but it's another way that we can use our instruments to look for signs of life. So I hope you're now just as excited as I am about the Perseverance mission. This mission is going to be able to tell us so much more about Mars than we already know. Even though we've studied Mars for many, many years, we're going to get knowledge from Perseverance that was never possible before. And in particular, the sample return is really going to be the next step in Mars research. And Katie will be able to tell you a lot more about that. But it is really a huge leap from what we've done in the past. And it's just the next stepping stone to our ultimate goal, which is putting humans on Mars. Once we understand what the surface of Mars really is like and whether or not there ever was life there, we'll be much better equipped to send humans there for a visit or maybe even longer.
from the Red Cliffs of Utah. I'm excited to be speaking to you today from a landscape as breathtaking as those we might expect to find on the Red Planet. On February 18th, 2021, just under 6 months from now, the Mars 2020 Perseverance rover will land on the surface of Mars at a very special place called Jezero Crater. Perseverance is NASA's next flagship mission to Mars and the first step of a multi-mission campaign to return samples from Mars back to Earth. Now, we've sent quite a number of orbiter and landed missions to Mars during the past few decades, and Perseverance will soon join this family of distinguished robotic explorers. But we can and should ask, why Mars? Why this mission? And why now? Mars today is inhospitable to life as we know it, but we have abundant evidence now that the surface of Mars was once habitable, possibly even Earth-like, between 3.5 to 4 billion years ago. There may indeed be niche, ephemeral, habitable environments on Mars today, like deep in the subsurface, but we think that our best chance of finding evidence of life on Mars will be in the most ancient rocks on the planet, likely in the form of what we call biosignatures, which are patterns, textures, or substances that require life to form. And why do we think there might be signs of ancient life in 3.5 to 4 billion year old Martian rocks? Well, it just so happens that the oldest accepted evidence for life on Earth is found in 3.5 billion year old rocks too. And we know that life must have emerged on Earth earlier than that. But searching for ancient life on Earth is actually pretty challenging, since our planet has a pretty limited record of this period of time. Thanks to plate tectonics, the Earth's crust is constantly recycling, and much of this ancient record on Earth has actually been destroyed. But we don't have plate tectonics on Mars, and as it turns out, about half of the Martian surface is older than 3.6 billion years. That means that Mars offers us a unique window into what a habitable planet in its infancy looks like. The most ancient rocks on Mars allow us to study a time period during which some of the most drastic changes in planetary and solar system history occurred, including the time period when life emerged and took hold here on Earth, and might have emerged on Mars as well. Of course, one of the main drivers for our continued exploration of Mars is to understand whether life ever arose beyond our own planet. And based on what we know of early Mars, the Red Planet is perhaps the best place in the solar system to ask and answer this particular question. But we're also interested in understanding the nature of prebiotic environments. What are the conditions and factors that led to the emergence of life on a planet? Mars, with its pristine and extensive record of early solar system history, offers us the ideal natural laboratory to study and answer these fundamental questions. Our interest in Mars goes beyond just the life question, though. We're also interested in understanding what we call chronology on Mars. Many of you are probably familiar with Earth's own geologic timescale, but by comparison, our understanding of the geologic history of Mars is fairly rudimentary. We have a lot to learn about the timing of major events on Mars, including impact events, volcanic activity, and the timing and duration of water at the surface. When did Mars lose its magnetic field and atmosphere? And how and when did those planet-wide changes really begin to affect the habitability of ancient Mars? Our current understanding of the timing of events in Mars's geologic past is based largely on crater chronology, a method of dating surfaces on Mars that has been extrapolated from what we know about cratering rates on the Moon, as well as absolute ages measured from samples brought back by the Apollo missions. But unfortunately, this method is imperfect, especially for a planet like Mars with a thicker atmosphere and once active surface processes that have modified that cratering record. So what we're really after is absolute age dates for Mars. But absolute age dating requires isotopic analyses and instrumentation that we're just not yet prepared to send on a rover or a lander. Finally, we'd like to know more about the evolution of Mars as an entire system. the analysis of isotopes using ever more sensitive and high-resolution instrumentation on Earth has led to a revolution in the understanding of the complexities of our own planet and its interdependent feedback loops. We'd like to understand the evolution of major elemental reservoirs on Mars over time, like the carbon, sulfur, and oxygen cycles, which will provide critical insights into the interactions between the planet's interior, surface, and atmosphere. By making progress in this area, we'll also better understand biotic or biological versus abiotic processes and what those signatures look like in the ancient rock record of Mars. But in order to make progress in these key areas, the planetary community determined about a decade ago, in what we call the last decadal survey, that Mars sample return was the highest priority science objective for the future of planetary exploration. As a result, a Mars exploration and sample collection rover was deemed the highest priority flagship mission for development. From this prioritization, the Mars 2020 mission was conceived, and development began shortly after Curiosity's successful landing in 2012. While many believe that Mars sample return is incredibly important and essential to make advances in our understanding of life beyond Earth and how planets evolve over time, some have made the case that we already have sample return. We do, after all, have over 250 confirmed Martian meteorites in our collection here on Earth. Why do we need more samples from Mars? Well, as it turns out, these meteorites are almost all igneous in origin, with surprisingly little lithological diversity. Our collection of Martian meteorites also records very little in the way of diverse surface processes, and there has been no evidence of Martian life found in them, although ALH 84001 certainly caused a stir in the late 1990s.
Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered.
But Martian meteorites also completely lack geologic context. Some scientists have speculated about where these meteorites might have come from and which impact crater on the surface of Mars they might have been associated with, but ultimately, we just don't know. And it's hard to make further progress on some of the major scientific questions that we have for Mars with this set of samples alone. And so Mars sample return, beginning with the Mars 2020 Perseverance mission, seeks to fill these major gaps in our scientific knowledge. To do this, the Mars 2020 mission has 4 main objectives. Like the MSL Curiosity rover currently exploring Gale Crater, Perseverance will characterize the geology and habitability of its landing site. We seek to understand the depositional processes responsible for creating the rocks that the rover observes, and to determine whether the conditions these rocks have experienced after they were deposited might have affected their ability to host and preserve life. We're looking for a record of ancient environments where all the building blocks required by life as we know it here on Earth can be found. The MSL Curiosity rover has spent the last 8 years doing just this in Gale Crater, and that mission provides a great example and template for how Perseverance will go about achieving this particular objective. But Perseverance will go a step further, specifically seeking to identify signs of ancient life in the rocks of Jezero crater. While other missions, and one could argue almost every Mars mission, has been searching for signs of life, the missions we've sent to Mars in the past haven't necessarily been equipped with the right payload for making these observations. While any rover or lander we've sent to Mars in the past would have been capable of imaging the proverbial Martian dinosaur bone if we were to find it on Mars, we don't necessarily expect that that's what ancient Martian life looked like. It's only been relatively recently in the geologic history of our own planet that complex life, like humans and dinosaurs, developed at all. So we expect that ancient Martian life, particularly early in Mars' history, if it was ever present, would be more likely to be of the microbial variety. Now, Nina talked through the details of the science payload already, but I'll just reiterate here that Perseverance is uniquely well-suited and more so than any rover or lander that we've sent to Mars, to seek and identify potential Martian biosignatures in the ancient rock record of Mars. For the first time on Mars, we'll have the ability to spatially resolve and correlate textures, geochemistry, mineralogy, and organics in the rocks that we study at very fine scales. This is exactly how we go about making the case for potential biosignatures in ancient rocks on Earth. But the reality is that while we may be able to identify potential biosignatures using the rover's in situ instrument payload, we'll very likely need to bring those rocks back to Earth to make a definitive determination of whether they contain evidence of Martian life. And that's where the mission's third goal comes into play. The first two mission objectives are in direct service to the mission's third, which is to prepare a cache of scientifically compelling, returnable samples. To accomplish this, Perseverance carries a brand new sampling system, which is one of the most complex robotic systems ever developed and sent beyond Earth. Perseverance carries 43 tubes, and we anticipate collecting at least 30 rock and regolith samples for science purposes. Our goal, first and foremost, is to put together a cache of samples with the best potential for containing signs of ancient Martian life. But we also seek diversity in the rocks that Perseverance will collect. Diversity is important because these samples, when they return to Earth, will be used by what's likely generations of scientists to address a wide range of important questions about the evolution of the planet Mars and its habitability. And we just simply can't answer all the questions we hope to address with just a single sample, even if that sample has signs of life, or a single type of rock samples. So it's important that we include a diverse range of rocks within that sample cache. Doing this also increases our chances of finding ancient Martian life if the samples we collect with Perseverance represent diverse habitable environments. Mars 2020's fourth objective is to prepare for future human exploration of Mars, and this has been a goal of other missions as well. There are several engineering updates and technology demonstrations, some of which Nina already mentioned, that advance our goal of sending humans to Mars. Although we've learned an incredible amount from our successful robotic exploration of Mars and the rest of the solar system, sending humans to Mars is a natural next step as we push the boundaries of our ability to explore beyond Earth. The Perseverance rover is the most capable and sophisticated rover we've ever sent to Mars, so it was really important to find the right place for the rover to carry out its mission, and to be worthy of its mission objectives. This site will also likely be the focus of Mars exploration for the next decade, so the landing site had better be fantastic. So over a 5-year process beginning in 2014, NASA and the Mars community considered several sites of prime Martian real estate. we started with more than 60 proposed sites on Mars and eventually narrowed it down to 3 sites and 4 possible landing ellipses. When looking for the right landing site for the Mars 2020 mission, we were first and foremost looking for a habitable ancient environment. At each of the candidate sites, we were looking for rocks that were formed or altered under conditions conducive to biosignature preservation, if that life had ever been present on Mars. We were also looking for a diversity of rock types to enable exploration of the wide range of compelling scientific questions that we have about Mars and for the purposes of Mars sample return. The 3 sites under consideration were Jezero Crater, an ancient delta and lake with diverse mineralogy, Northeast Syrtis, a site with ancient crust with past volcanic and impact activity, and Columbia Hills, the site of the Mars Exploration Spirit Rover, and an ancient hot spring with potential biosignatures. Now, each of these sites represented a different but compelling ancient environment where life might once have existed on Mars. But ultimately, NASA and the Mars community felt that Jezero Crater was the best place to send Perseverance. Now, Jezero is special for a number of different reasons and worthy of the mission that Mars 2020 is going to carry out. It's located on the inner western rim of the Isidis Impact Basin, one of the largest and oldest impact basins on the surface of Mars that's been dated to about 3.9 billion years. Also nearby Jezero is the Syrtis Major Volcanic Center to the south. These volcanics have been dated to between 3.5 to 3.8 billion years. So what's great about Jezero is that we can already, based on what we know about the geology of this area of Mars, constrain the age of the rocks in Jezero to be younger than Isidis, 3.9 billion years, but older than the Syrtis volcanics, 3.5 to 3.8 billion years. And this interval of time is exactly that period of time when life was emerging on Earth. So the rocks in and around Jezero will provide us access to a preserved record of this really critical time in the solar system when life could have been emerging on Mars, just like it was here on Earth. There are a number of ancient crater-like basins on Mars, but Jezero distinguishes itself by having both an inlet valley and an outlet valley. Most craters we observe only have that inlet valley, so we know that water flowed into the crater, but we don't know how much water or for how long it was there. But in Jezero, we know that the entire crater filled up to the point where water eventually spilled over the rim. And this is how we know that there was a standing body of water in that crater for a geologically significant period of time. Jezero has within it one of the most beautifully preserved deltas on the surface of Mars. So deltas are landforms that form when rivers enter an open body of water, and they're the ideal deposits for preserving organics and other evidence for life in these deep, low-energy environments that are far out into the basin. The Jezero Delta is truly fantastic in that we can see and observe the sedimentary facies that represent different parts of the delta in images taken from orbit that we have already. So we have a huge leg up on understanding the environments present in Jezero Crater before we even get there with the rover. There are also coarse river deposits on the top surface of the Jezero Delta, whose pebbles and boulders are sourced from the extensive watershed outside of Jezero. The rivers that flowed into Jezero did the hard work for us, collecting these diverse rocks from outside the crater, transporting them into the crater, and depositing them in the layers of the delta. Now we just have to go and find those rocks with Perseverance. Investigating these river deposits will be our first opportunity to encounter those really ancient rocks that formed the Martian crust beyond Jezero Crater. So much of the Perseverance ellipse within Jezero covers a unit that we call the mafic crater floor. Now, scientists have hypothesized that this particular unit could be an ancient lava flow, which would be ideal for obtaining absolute age dates, as well as telling us about the nature of volcanism on Mars, which we think was a major process in Mars's ancient history. But others have speculated that this unit could be sedimentary in origin, so we have some questions to answer on the surface with Perseverance, but that's of course what makes it exciting to send a rover there. Also exposed on the crater floor is an olivine-bearing unit that is similar in composition and morphology to a unit present across much of the region west of the Isidis impact. We're not entirely sure what this unit represents, or how it was deposited, but examining it here in Jezero Crater will provide insights into a regionally important process on Mars. But one of the most compelling astrobiology targets within the crater, aside from the delta, of course, are deposits located along the inner rim of Jezero. These deposits contain carbonate, a mineral that can preserve a record of surface-atmosphere interactions in the deposits that it forms. Carbonate is a mineral that we're familiar with here on Earth that is commonly associated with biotic processes, and you might be thinking about carbonate reefs in the Bahamas. And it's also great for preserving evidence of life. Now, we may not have reefs like the Bahamas on Mars, but the carbonates in Jezero occurring along those inner margin are exactly where we might expect a shallow lake margin to be. And that's a place where microbial life would have had all the ingredients to survive and thrive. So we're really excited to go check those out. Finally, in the Jezero crater rim, we observe megabreccia, composed of house-sized blocks formed either during the Jezero or Isidis impact events. These blocks could represent pre-Isidis crust that is more than 4 billion years old, and some of the oldest rocks in the entire solar system. But thinking back to the criteria that we had for a landing site worthy of the Mars 2020 mission, where Jezero really hits it out of the park, is that if this same environment that we have in Jezero were found here on Earth, it would absolutely be habitable. So we're optimistic that this site on Mars has the potential to answer some of our biggest questions about life beyond Earth. We also have mature models to guide our exploration and sampling in a delta lake setting. We know a lot about deltas from our studies here on Earth, and we know exactly where in a delta to go to search for biosignatures. With the ambitious sampling goals that Perseverance has, this advanced understanding of the landing site will allow us to carry out the mission as efficiently as possible. If the rover is healthy when it has completed its exploration of Jezero crater, there is the potential for the rover to traverse beyond Jezero, out to the plains of northeast Syrtis, one of the other finalists in landing site selection. Here, the rover would encounter in-place ancient Martian crust and explore a variety of additional habitable environments, including those that were once deep underground, now exposed at the surface today. By visiting these locations within and around Jezero, we believe we can put together a diverse cache of samples that will address the wide range of compelling scientific questions, including, was Mars inhabited? How did rocky planets form and differentiate? How did the surface environment and climate evolve on Mars? The samples that Perseverance collects have the potential to tell the story of a planet, from a time it was once habitable and possibly hosted life, following along on its journey down a drastically different path than our own planet Earth into the barren wasteland it is today. Perseverance is currently in cruise on its way to Mars, and at the time I'm recording this talk, has now traveled more than 50 million miles along its 292 million mile long journey to Mars. The rover will land in Jezero on February 18, 2021, and by this time next year, we'll be writing up our initial mission science results and may very well be preparing to acquire our very first sample of Mars. Thank you for listening, and we'll see you again when Perseverance lands on the surface of Mars in February.
My name's Andrew Jones. I'm a freelance space journalist with the specialization in following China's space activities. So I'm going to give a brief overview of China's Tianwen-1 Mars mission, which is China's first independent interplanetary mission. So a quick bit of background. The mission was approved in early 2016 and has now been named Tianwen-1, which comes from a poem from a famous poet named Yuan from the 4th century BCE. And so after a relatively short development time of around 4 years, China's mission launched on July 23, 2020 on a Long March 5 rocket from the Wenchang Satellite Launch Center.
我们叫助推飞行段，这段时间段主要是火箭尽快加速，火箭加速到。
现在我们看到这个画面还是从地面拍到的我们长午的这个。
So the Tianwen-1 mission is around about 5 metric tons altogether in terms of wet mass, so that includes propellant for the spacecraft. And the spacecraft is a combination of both an orbiter and a rover, which is destined for the Martian surface. The spacecraft has so far been healthy on its way towards Mars. It's carried out 2 transfer correction maneuvers. A third of these is to come in the following months, and a more powerful deep space maneuver is also scheduled, possibly in October. The spacecraft also recently jettisoned a small camera which managed to take 2 pictures of the spacecraft and transfer those back to the spacecraft using Wi-Fi, which were then beamed back to Earth. So we've got images of the spacecraft in deep space. Arrival at Mars is expected in February 2021, and first the spacecraft will go into an elliptical Mars orbit and prepare for the landing attempt, which might not come until April or May that year. So we'll have a few months in orbit while the spacecraft images the targeted landing area in Utopia Planitia in the northeast of Mars. So when the landing attempt takes place, the rover inside a protective aeroshell will separate from the orbiter and shortly after enter the Martian atmosphere. The aeroshell will protect the spacecraft as it makes a high-speed entry into the atmosphere and then be jettisoned. A supersonic parachute will then continue to slow down the spacecraft as it moves through the atmosphere. The final section will be retropropulsion, which will make the final deceleration down onto the Martian surface. So these technologies are borrowing from heritage from the Chinese Shenzhou human spaceflight missions, and also in terms of the parachute, and in terms of the retropropulsion and the lander, it will be borrowing from the Chang'e 3 and Chang'e 4 missions, which landed on the moon in 2013 and 2019 respectively. So the rover is about 240 kilograms, which is roughly about twice the mass of the Chinese lunar rovers. It will be solar powered and has a design life of around 90 Martian days, which works out to around about 93 Earth days. So during this time, the orbiter will be acting as a relay for communications back on Earth. To facilitate the mission, China also had to make breakthroughs in its ground station capabilities. So it has a large new station at Tianwen in Argentina, as well as larger dishes in Tianjin in North China and facilities also in Northeast China and in the Northwest. China originally chose 2 candidate landing areas on Mars. It's now narrowed this down to the second landing area, which is around the Utopia Planitia landing site, which is just to the south of the Viking 2 landing site. China Aerospace, an official Chinese newspaper, actually published some coordinates for the landing. These were noted to be 110.3.18 degrees east and 24.728 degrees north, which gives a very precise target area for the landing. So this prospective landing site actually offers a lot of interesting possibilities for science. The area is covered in aeolian ridges, which are a type of sand formation which are particular to Mars. The overall science objectives of the mission have been stated in Chinese papers to include studying the topography and geological features of Mars, also the investigation of the physical field and internal structure of the planet, the studying of the atmosphere, ionosphere, surface climate and environment, the ascertaining of surface material composition, and also studying the soil characteristics and water ice distribution. Overall, the two spacecraft carry 13 science payloads. There are 6 on the rover, which are a topography camera, a navigation camera, a rover-based Martian subsurface penetrating radar, which is similar to the ground penetrating radars carried by rovers on the Chinese Chang'e 3 and 4 missions, a surface composition detector, a multispectral camera, a magnetic field detector, and a Mars climate detector are the other instruments on board. The orbiter carries 7 science payloads. These include a medium resolution and a high resolution camera for mapping Mars. The high resolution camera will be similar in capabilities to the high-rise camera on Mars Reconnaissance Orbiter, and therefore will be one of the more powerful cameras ever sent into deep space. Also aboard are a Mars mineral spectrometer, a magnetometer, a ions and neutral particle analyzer, and an energetic particle analyzer. The final payload is a sounding radar, which will provide yet another look into the subsurface of Mars. So this instrument will be similar to the Charad instrument aboard the Mars Reconnaissance Orbiter, and also the Marsis payload on the Mars Express from ESA. However, this will be operating on a slightly different frequency, providing a different resolution and another look at the subsurface. So we may well be getting more evidence or even further identifications of new subsurface lakes which may be filled with liquid water or briny water. I mentioned at the very beginning that this is China's first independent interplanetary mission. The first attempt that China made actually came in 2011 with the small Yinghua-1 orbiter. Now that launched along with the Russian Phobos Grunt mission, which was attempting to collect samples from the Mars moon Phobos and return them to Earth. Now unfortunately, the spacecraft failed to leave Earth orbit due to a failure with the upper stage of the rocket. So both Phobos Grunt and Yinghua-1 ended up burning up in the Earth's atmosphere. In terms of following the mission, there have been regular updates from China on the progress of the spacecraft, but these have been generally small things like the distance from Earth and the total flight distance. However, the major milestones such as the upcoming deep space maneuvers, these are not announced ahead of time in terms of when they will happen. Indeed, also the landing attempt, we don't know when that will happen. We also don't know for sure when where the landing will take place, although there are hints and clues as I mentioned. So following Chinese state media is one way to keep in touch with the latest with what's going on, and also more specialized accounts on the Chinese social media platform Sina Weibo. Myself, I also tweet very regularly on this mission and all other Chinese space activities at AJ_FI on Twitter. And if you have any questions, you can contact me via email or on Twitter, and I'll be happy to help out. Thanks very much.